We ready? There we go. Oh, you see they bounced.
Okay, so this is the experiment that was supposed to be an inelastic collision where they should stick together but they bounced. Now Gary claims victory because car 2, which is twice the mass, comes out with less than half the velocity and therefore it proves his model right. However, Gary makes the wrong claim that this is a real elastic collision because no spring or rubber band was used. And no, this is not an ideal elastic collision. This is a partial inelastic collision. More explanation later in this video.
So no springs, all right? So it's going to be a real elastic collision in the sense that they're going to bounce honestly, no spring to create the backwards direction.
We use springs or rubber bands in elastic collision experiments because they can undergo large deformations and recover their shape without losing significant amounts of energy, making them ideal for demonstrating conservation of kinetic energy. When we do collisions without springs, so surface to surface or metal against metal, part 1 will most likely not bounce back. It will either stop or move in the same direction after collision. Now here are a couple of examples done by Stephen Bro.
I'll do this one first of all. Green to red, so to speak. Green to red. Ready? Now basically trigger it from this end. You might not see that part. Okay, so
And here are some examples done by myself. This is a collision with a spring attached to it. As you can see, part 1 bounces back. So this one is a little bit heavier. With the spring, part 1 bounces back. Without the spring, so now metal to metal, or surface to surface. Part 1 stops or moves a bit in the same direction. See, now it moved a little bit into the same direction after collision. So this is always what happens when we have metal to metal or surface to surface. So metal to metal collisions are not ideal elastic collisions. They are partial elastic collisions. And in Professor Lewin's case, it's a partial inelastic collision. And so to determine whether a collision is either elastic, inelastic, or partially elastic or inelastic, we have to measure how elastic a collision is. And this is called the coefficient of restitution, E. Here you can see the formula for the coefficient of restitution. And so more importantly, when E equals 1, then we have a perfectly elastic collision. So no kinetic energy is lost. The objects do bounce off in the opposite direction. When E is 0, then we have a perfectly inelastic collision. So the objects stick together after collision. Now, when E is between 0 and between 1, then we have a partially inelastic collision. So some kinetic energy is lost, but the objects don't stick. So to know the coefficient of restitution is important to predict the velocities of the cards after collision. Now, since Professor Lewin's failed inelastic collision is actually a partial inelastic collision, the coefficient of restitution will be between 0 and 1 rather than 0 or 1.
So 100 went in, 85 is going out. In the previous experiment, 100 went in and 133 went out. So it's way short of that. And it's just a coincidence, though. Don't pay any attention, just a coincidence.
No, it's not a coincidence. In the other experiment where car 2 came out with 133 momentum, that was a perfect elastic collision where the coefficient of restitution was 1. And in this experiment, the coefficient of restitution is less than 1. So no, it wasn't supposed to come out with 133 as momentum. Also, in a perfect elastic collision, yes, after collision, mass 2 should lift off with 2/3 of the initial velocity and mass 1 should bounce back with 1/3 of the initial velocity. But since the coefficient of restitution is less than 1, the predictions of the velocities will be different, and also the directions. Notice how cart 1 continues in the same direction after collision.
We ready? There we go. Oh, you see they bounced.
Now what do we know about carts moving in the same direction after collision? Yes, we have to add the momenta together. So if we assume that the flags on the carts are 10 centimeters wide, then we get for V1 the velocity is 0.090 meters per second, and for cart 2 the velocity is 0.036 meters per second. So now the initial momentum of cart 1 before collision is 0.090 kilograms per times meters per second, and the momentum for cart 2 after collision is 0.072 kilograms times meters per second. So the initial momentum was 0.090, and then cart 2 came out with 0.072. So that there is a difference of 0.018. Okay, so we have lost 0.018 momentum, but that momentum is actually of cart 1 still going in the same direction. So when we add 0.072 plus 0.018, that will add up to 0.090. Now, can we prove that? Well, unfortunately, Professor Lewin stopped cart 1, preventing it from going through the second photo gate. So we don't know the exact timing of cart 1 after collision. However, it is most likely that the momentum that we have lost, so this 0.018 indifference, that is possessed by cart 1 going in the same direction. Even Gary agrees with this, that the rest momentum is possessed by the cart 1 still going in the same direction.
And clearly the one cart's following the other cart, so that's where the rest of the momentum is, the part that's missing, the part that's short of half the velocity. So the higher the...
Yes, and the rest of the momentum, so the 0.018 kilograms times meter per second, is going in the same direction, so we have to add them together. Momentum is also conserved for conventional signs. I have pointed this out before. When both carts continue to move in the same direction, momentum is conserved for both draft signs and conventional signs, because we have to add the momenta. However, it is always a conflict for you when one of the carts move in opposite direction, because oh dear, then we have to subtract momenta, and since momentum is energy according to you, of course momentum cannot be cancelled. So there you go, debunked once again.